Assalamu alaikum everyone, my name is Abdullah and I'm going to present you today classification of chili plant growth using deep learning for IEEE International Conference on System Engineering and Technology in 2020. The cultivation of crops in greenhouses under specified conditions has received great attention due to the high food demand by the increased population. The chili plant growth monitoring in Malaysia still performed manually by human laborers which consume a lot of time and energy, and the plant growth can only be monitored on site. Cultivation, convolutional neural networks, one of deep learning approaches, has become a powerful tool for tackling images problems and can even instantly detect and separate objects from complex background. Being able to monitor the growth of plants using CNN-based methods will eventually help to achieve the two major goals. The first goal lies in achieving maximum growth rate while lowering necessary energy consumption and providing an opportunity to monitor the growth rate as a function of environment conditions. The other goal is associated with growth control and fruit production. By monitoring the growth of every individual plant, one can easily check plant health and find out abnormal ones, which leads to a better estimation of fruit quality and the final production. The problem statement of our study touches four main points. Firstly, the study on the automatic chili growth monitoring in greenhouses has not been properly investigated in Malaysia. Secondly, the growth of chili plant is monitored manually by human laborers. Thirdly, the process consumes a lot of time and energy. And lastly, the monitoring can only be performed at site. Objectives of our study touches three main milestones. First is to identify the methods to develop the proposed deep learning based for chili plants growth monitoring system, to design and develop the proposed monitoring system, and lastly, to evaluate the performance of this system. The method that we have chosen for this study is mask RCNN. This method was proposed in 2017. It was based on faster RCNN for instant segmentation and object detection. This method has extra branch for protecting segmentation mask as an output for each detected object. Mask RCNN method outperforms all current methods in the community in all three tasks of Coco Challenge: instant segmentation, object detection, and person key point detection. Mask RCNN, as you can see in this architecture, has mainly two stages. Both of the stages are connected to a backbone structure, and we will use two main backbones, ReasNet 50 and ReasNet 101. The first stage, a lightweight neural network called Region Proposal Network, RPM, scans all future pyramid network and proposes regions that may contain objects. RPN uses slide window method to produce anchors, and anchors are a set of boxes with predefined locations and scales relative to the input image. Ground truth classes and bounding boxes are assigned to individual anchors according to some intersection over union IOU value. As anchors with different scales bend to different levels of feature map, RPN uses anchors to figure out where of the feature map should get an object with what is the size of the object and what is the size of of the bounding box of that object. In the second stage, another neural network takes the proposed regions by the first stage and assign them to several specific areas of a feature map, scans these areas and generate object classes, bounding boxes, and masks. This second stage uses a method called region of interest align to locate the relevant areas of feature maps. Uh, the first stage of our study, we have data collection. In data collection, we have used iPhone 8 smartphone to take images for chili plants at the age of week 10 and week 14. These images were taken for two view, top view and side view. For the side view, it was taken from a distance of 150 centimeters, and for the top view, 230 centimeters. And this was to make sure that all of the plants are in the images, in their images. And to have the biggest amount of data set, we have applied some effects on our collected data. So for the side view images, two effects were applied: mirror effect and brightness change. As you can see, in the left image is the original image, and the middle one is the mirrored image, and the last one on the right is the brightness changed image. And for the top view images, vertical and horizontal mirror effects were brightness change and rotation by 90 degrees, 180 degrees, and 270 degrees were applied for these type of images. As you can see, the top left image is the original image. The one beside it is the image rotated by 180 degrees. The one on the bottom left is the image, the mirrored image under the mirror effect, horizontal mirror effect. And the last one on the bottom right is the brightness change image. And all of the dataset were resized to 1024 by 1024 pixels. Yeah. So in total, as you can see in this table, we got 256 images for each class. The side view week 10 got in total 46 images, and top view week 10 64 images. Side view week 14 64 images in total, and the last one is top view week 14, also 64 images. And to prepare our data set for training, we used image attenuation tool VIA to create the mask for each object in each image. And the classes, as we have said before, and as you can see on the left. And these two examples of the masks that were created manually by this tool. Thirdly, for training and testing, we have used 75% of dataset for training and 25% of dataset for testing, with 17 epochs and 256 steps for each epoch. The hardware that was used is CPU of Core i9 ninth generation, memory 32 gigabyte of memory, and for GPU we have used NVIDIA GeForce GTX 1650 with 4 gigabyte of graphical memory. As for software, we have used Python 3, Keras 2.2.5, and TensorFlow 1.14. And as you can see on the right, these graphs describe the training and validation losses for each epoch. And this was calculated based on the class loss, mask loss, and bounding box losses. So yeah. As for our results, we have two models. The first model is mask RCNN ReasNet 101, and it achieved accuracy of 96 in total. And the problem that this model had was with side view week 14. Some of the images were not detected. Some of the objects were not detected. But for the other classes, all of them were detected successfully. As for the second model, mask RCNN ReasNet 50, almost all of the objects were detected successfully. However, we had an issue with also side view week 14. Some of the objects were not detected. And this accuracy of this model 97.25%. The issue that we had with both of the models, some of the images, some of the plants in week 14 were not detected at all in the first time. So when we redid the detection for the second or the third time, it was detected successfully, as you can see in the image on the left. But this was an issue, and we considered only the first attempt of detection. That's all. Thank you very much for listening. Assalamu alaikum wa rahmatullahi wa barakatuh.